Welcome to this explainer. Today we're doing some serious chemical profiling. We are taking a micro to macro journey through Unit 3, acids, bases, and the pH scale to get you completely ready for your exam. If you've ever wondered why certain chemicals behave the way they do, or how they interact at a foundational level, well, we're going to break it all down visually for you right now. Let's get into it.
Here's our game plan for today. Defining acids and bases, conjugate acid-base pairs, strong versus weak acids, calculating the pH scale, and finally, understanding titration curves. Section 1. Defining acids and bases, 3 historical theories. Okay, so looking at this side-by-side comparison, you can really see how our understanding evolved over time. It's kind of like a chemical history lesson. First up, the Arrhenius theory focused strictly on water, defining an acid as producing H+ ions, like HCl or nitric acid, and a base as producing OH- ions, like sodium hydroxide. Then, Brønsted-Lowry came along and viewed it more as a molecular game of proton catch, where acids are H+ donors and bases are H+ acceptors. Finally, the Lewis theory brought in the whole shebang to electron matchmaking, identifying acids as electron pair acceptors and bases as electron pair donors.
So the absolutely crucial takeaway here is that a Brønsted-Lowry acid's entire identity is based on its ability to give away or donate a proton. That single H+ ion transfer, that's the foundational engine driving literally all the reactions we're about to look at. Moving on to Section 2, Conjugate Acid-Base Pairs, the proton catch game.
This reversible reaction right here perfectly anchors what we were just talking about. It shows a live-action chemical game of catch. Ammonia reacts with water to yield ammonium and hydroxide. And those double arrows in the middle, they're just a quick reminder that this is a dynamic equilibrium, meaning the reaction is flowing in both directions at once.
Notice how we can link these molecules across the reaction. Pair 1 hooks up NH3, the base, with NH4+, its conjugate acid. Pair 2 connects H2O, acting here as the acid, with OH-, its conjugate base. You see how each pair differs by just one single proton? By accepting a proton, the base transforms into its conjugate acid, and by donating a proton, the acid transforms into its conjugate base. It's a perfect swap.
Now, while we're looking at reaction equations, here is a huge, and I mean huge, exam key. If you see a single arrow instead of that double equilibrium arrow, it means the reaction predominantly proceeds in one direction. It is a one-way street, not reversible under those conditions. This usually indicates that something, like weak base ionization, is so slight it effectively only moves forward.
All right, Section 3, Strong versus weak acids, chemical power levels.
This comparison highlights a massive behavioral difference. Strong acids represent absolute commitment. Substances like hydrochloric or perchloric acid completely ionize in water. Because they totally break apart, they generate a huge concentration of H+ ions, which makes them fantastic conductors of electricity. On the flip side, you have weak acids, like acetic acid, which only partially ionize. This partial effort gives you a lower H+ concentration and consequently makes them pretty poor electrical conductors.
Now, beyond sheer strength, acids are also classified by their chemical ammo. I mean, how many protons can they actually fire off? Monoprotic acids, like hydrochloric acid, donate just one H+. Diprotic acids, like sulfuric acid, have 2 protons to give. And triprotic acids, such as phosphoric acid, they are fully loaded and ready to donate 3 H+ ions into the solution.
Next up, Section 4, Calculating the pH scale, measuring intensity.
Looking at the entire spectrum of acidity and basicity here, notice how it's organized. The scale runs from 1 to 14. An incredibly important rule to remember is that a lower pH actually indicates a stronger acid, which you'll see heavily clustered in that 1 to 3 range. A pH of exactly 7 is perfectly neutral, and as you exceed 7, climbing all the way up to 14, you're getting into the territory of the strongest bases.
Let's actually test this mathematically, with a quick calculation directly from our source material.
If the hydronium ion concentration, that's the H3O+, is 10 to the -4th molar, what's the pH? Think about it. If we plug this concentration into our standard formula, where pH equals the negative log of H3O+, what do we get?
The answer is exactly 4. The negative log of 10 to the -4 drops that exponent right down to a positive 4. This mathematically proves that this specific solution is acidic, since a pH of 4 falls well below that neutral threshold of 7.
Finally, Section 5, Understanding Titration Curves, Lab Applications.
Okay, so a titration is essentially a laboratory method used to hunt down the concentration of an unknown acid or base. And the entire goal? Reaching the equivalence point. This is that magic exact moment where the moles of acid equal the moles of base, meaning every last bit of the acid is neutralized. When you're titrating a strong acid with a strong base, this exact moment of total neutralization lands perfectly at a neutral pH of exactly 7.
And this brilliantly lays out the chronological story of a titration curve in 3 distinct acts. Step 1, before the equivalence point, excess acid is totally dominating the solution, keeping the pH super low. Step 2, right at the equivalence point, we achieve exact neutralization at a pH of 7. And finally, step 3, beyond equivalence, where adding even a tiny little bit of excess base rapidly skyrockets the pH up the scale.
Now you might be wondering, why does the graph spike so suddenly at the end? Well, this specific quote hits the nail on the head and explains that massive vertical jump. Once all the acid is completely neutralized, there's literally nothing left in the solution to absorb the new base. The buffer capacity is totally exhausted. That means even minuscule, tiny drops of base will cause immediate, incredibly large pH changes.
It is honestly incredible to think that the exact same math and chemical profiling we just walked through governs massive environmental and biological systems all around us. So I'll leave you with this. How do these microscopic proton transfers, these tiny little chemical games of catch, shape everything from standard laboratory titrations to the delicate balance of our entire ocean ecosystem? It's a fascinating reminder of how the micro dictates the macro. Thank you so much for joining me for this explainer, and absolutely best of luck on your exam.